Do you know what is that? This equation is the one which we use for the ideal gas. And in fundamental physics. And you know that we derived this equation without any information about quantum mechanics or something. This is the first estimation. But I want to find C. Because not always all the equation will be independent like that and the C will be ignored. So we need to know the C, because after that, not only the pressure, I want to find the other parameter, like the enthalpy, like the Gibbs energy, like the free energy, Helmholtz, and everything. So I need to make this equation, this calculation more correctly. That was just approximation, estimation actually, or estimation. That was just estimation. But even this very, very, very handy estimation gives you the rule for the ideal gas, you know, just by counting, just a very easy idea. But I wanted to make it more effective. So for the more effective one, I need a bit quantum mechanics, but that's not also a big issue. Look at that. After this easy estimation, I will pass now to the quantum mechanics. So I will consider here the particle in the box. I back to this particle in the box, but with more detail. So, for the sake of the simplicity, I just consider a particle with a cubic box. So the volume is L cubic. Huh? Before any calculation, I know that the E and N of V will be some function of E and N multiplied with V power N. So I want just to find this. I want to see that what's the C. In very unusual way, I will find that. In very unusual way. You know that all E omega is about finding the possibility for localizing the particle in the different energy states. Huh? What's the energy state for the particle when it's moving freely in the box, and that the box is considered as the system, quantum mechanical system. So the potential for this system, you know that potential of the system will be hard wall actually if x, y, and z are between 0 to L, 0 elsewhere infinity. We consider that. So this type of the potential explicitly define the form of the wave functions. It shows that the wave function should satisfy this kind of the Dirichlet boundary condition. Yeah, you can repeat that for the other size. Zero, because particle cannot penetrate from a domain with the potential, infinity potential, so actually. And it's the same, you can write it for the Schrödinger equation for the region between the plate is just minus h power square, del square is equal to psi because there is no potential. So you can just replace this, rewrite this equation in the following form. And what's the name of this equation? This is a Helmholtz equation. Helmholtz equation in the mathematical physics. So you can find the solution of this by the separation of the variable, hopefully. So the side, I think this is something you know. So you can write it that this phi x as a function of this, phi y as a function of y, and phi 1 and 2 and 3, 1, 2, and phi 3 as a function of the z. And because of the separation of the variable, you can consider the total movement of the particle in the three independent directions. I mean that you can say that the particle is moving with the momentum p by p, px, py, and pz independent from each other in the three dimensions. So you know that the energy E will be Ex plus Ey plus Ez. This is a very confusing notation because it doesn't mean that the energy is the vector. So it was better maybe I write it that E1, E2, E3, but the index of the 1, 2, 3 we use normally for the energy level, no? E1, E2. So I needed to write like that. So just understand that the E is not a vector. It just shows that the part of the energy for particle and moving along the x-axis and the vector. So using this, you can substitute that here, and you will get d phi I ax squared chi squared phi 1, 0, and the same for the y and the z. Just change the x to y and the z. And using the Dirichlet boundary conditions, you can get that kx squared will be n squared p squared. You can get that phi 1 will be r1 sinus nax p along x. Nax will be, I will give you that just for handwriting that as the homework. You will do that. And the same for the other phi 2, for example, will be b1 sinus. No, but I don't give you that. I wanted to give you the same problem, but when you have a not Dirichlet boundary condition, you will have a Neumann boundary condition. I will explain what's that. I want to give you the same question and to solve for me later as a homework, but instead of the Dirichlet boundary condition, I will ask you to solve that by the Neumann boundary condition later. So this is all the quantum mechanics. So, and from here, you immediately get kx will be naxp alone, and same for the similar for the y and z. And because k squared is kx squared plus ky squared plus kz squared, so you finally will get the energy. So I wanted to write the final equation for the energy. For the one particle, yes, this is the energy for the one particle. So you have an n particles, so the total energy of the system will be just represented as a summation over the energy of the single particles. So the energy of the one particle EI will be ph by square 2m l square n x I square plus n y I square plus n z square. This I is for the particle number. Particle number. So what's the total energy of the system? Is sigma E I 1 to n. So will be phy square 2m. Let me from here. V is L cubic, so let me to write L V1 over K, because everything should be written in terms of the extensive parameter. Volume is the extensive parameter. I know the L is also extensive parameter, but in 3 dimension, talking about the size of the one direction, that's not a very good idea. put it S I. This is the total energy of the system. Huh? There is a one summation here, huh? 1 to 3. If I write Nxi as Nr, so this can be written as the Nr squared, huh? R1 to 3. Huh? And it will make it more compact equations. So sigma Nr squared, can I write this 1 to 3n? No. There is a one summation 3 running from 1 to 3, and there is a one summation running from 1 to n. For each particle, you have a 3 possibility. So it's running from the 1 to 3n. It should be total energy, 2me v over 3 p squared h4 squared. I don't know, by some reason people prefer to write that h over 2 pi squared and finally make it that 8m h squared ev 2 power 3. This equation, if can be solved, gives you the all configuration of the system. I mean, it gives you the all possible n for your system. Huh? And you are talking about how many? Yeah? How many configuration means that the possible solution for this equation. I will give you very lower dimensions case just to see. There is a very interesting here that the number of the possibility. So number of possibility is, I mean, we need to count the solution, the number of the solution for this pair of the n, you know, n1, n2, n3. Look, this is not very easy equations. You can have, for example, put 1, 1, 1, 1 here and just find the last one. Huh? You can do that. Yes?
Yes.
You can put this 1 and 2, 1, 2, 2, 2, 2, 2, 1, 1, 2, 1, 3, 1, 3, everything, you see? And then find the other one. As long as you have one parameter, this equation can be solved very easily. I mean, this looks like that is this equation, look. If you give me exactly the y and the z, I can find for you x. X will be plus minus r squared minus y squared minus z star squared. Yes? For each pair. So, if this is a n1 squared, n2 squared, n3 squared, r squared, look at that, this is for one particle, because this is going to 3n. I just put 1 here. If you have n1, with n1 you can find a lot of solution for that, many number of the solution. Why you are looking very doubtfully for that? You know, this is the, we are looking to know that how many solutions exist for this equation, okay? Each solution gives you one possible accessible state for your system. So, I told you that there is a very easy way. For example, you can put it 1, 1, 1, 1 all and just keep it the last one. You can keep it the one of the middle and just put it the other one, 1, 2, 1, 3, 1, 2. You see that there is it should be an easy way to count the number of the solution. So you will find that, you will find the solution like that. Look, I don't know, something like, but not, you don't think that this 1 is very important number. I just playing with 1. Put it the old one and just playing with to find the one of them. Like n1 star, not n2 star, so n1 star and 1, 1. This is a 1 strategy. But you can play it that and the n1 star and put it this 2 and play with 1. You see how many possibilities. Actually, we can't do this. It's a crazy game, actually. Just counting one by one how many possible solutions for this. And all of these all of this, what I can set of NR should satisfy this equation. Like that. How many x and y and z satisfy this equation? What does it mean? It's all the number over the surface satisfy this equation. All the point over the surface, exactly over the surface. So all the point on the surface of this sphere satisfy this equation. Okay, let me. So our task in the few minutes remaining from my lecture is just to show that how to find the number of the solution for this equation. You see that from the 3 dimension, what's the name of this? First of all, sigma nr square r from 1 to 3n is 2m 8m h square ev2 plus 3. Can I write it that r square? R square. If n is 1, so this is the, you know what is the sphere equation, Sphere. 1 ball. But that's we call it n ball. Yeah. 1 is 3 dimensional, so we have a 3n, so this is an n ball. You can't imagine that actually. Definitely you can't imagine. I will ask you how many possible solutions for this equation. As you understood here, all the solutions are located on the surface of that. On the surface of that. So if I can find the surface of the, or volume of that, the volume, because you know, there is no difference between the volume and the area here. Because n is big number, n is 10 power 23. So when the dimension of the sphere is 10 power 23, so it doesn't sense that you consider the surface of the volume. What's the difference between surface and the volume? Just one dimension. Just one dimension, yeah? If you have a sphere, surface is 2 dimensional. If you have a hypersphere or hyper surface, but the surface will be 1 lower dimension from the volume. So there is no big difference. This is the first point, because n is very big number. So the change between the volume, actually they are very similar to each other. Actually, not in this level, maybe because they are big number also. The ln of these 2 numbers will be the same. They are big number also, because n is big number. You don't have idea that how to calculate the volume of that or area of that. Just you need to know that because n is big, so I want to tell you that there is no big difference between the volume and the surface. So if you consider that, look at, if you consider that at the n bar, for example, I know that this picture doesn't make sense anything because we cannot imagine about n bar. Anyway, the volume of that, the volume will be something like Rn. Can you understand that? The volume of a sphere is R cubic. The volume of the circle is R square. The volume of the line is just R. So Vn is CRn. Then I make the differential from that. No, differential. So we needed to find the volume of that sphere, 3n sphere, with the r, and we hope that it will be very good approximation for the omega. Omega was the number of the possibility or accessible state in your system. And as I explained to you, it is related to the counting the number possible solution for this equation, as I got it. And this number is very huge, but from the 3 dimension, we have this idea that the number will be related to all the points on the surface. If I can estimate the surface, I will have estimation about the number of the accessible state. And as I use the trick, I told you that because n is very big, so there is not big difference between the logarithm of the volume or logarithm of the surface if you are in the large number of this. Before I do calculation, I want to tell you one thing, that omega